Welcome back to the Deep Dive. For all you number theory students listening, we're continuing our journey through the Online Encyclopedia of Integer Sequences, the OEIS.
Always a fascinating place.
It really is. And today, we're tackling a particularly interesting one. OEIS A000311. It's known as Schroeder's fourth problem, dealing with labeled series-reduced trees.
That's the one.
So our mission today is basically to unpack this sequence, see how just one string of numbers can, link up worlds as different as biology and network design. It sounds intriguing.
It absolutely is. There's a lot packed into A000311.
All right, let's dive in then. Where do we start?
Well, at its core, A000311 gives you the number of labeled series-reduced rooted trees that have exactly n leaves.
Okay, labeled series-reduced rooted trees. Let's break that down a bit. What's series-reduced?
Right. So series-reduced is key. It basically means these trees don't have any simple single branches coming off a node, no unary branching, meaning every node that isn't a leaf, every internal junction point has to connect to at least two other nodes or leaves below it.
Oh, okay. So it has to split. It can't just continue as a single line.
Exactly. It forces a certain complexity in the branching, and the root itself either has degree 0, meaning it's just a single point for n1, or it branches out into two or more subtrees.
Got it. So that's the primary identity. But you mentioned connections.
Yes, and this is where it gets really interesting. The sequence also counts something called total partitions of n.
Total partitions. How does that work?
Imagine you have the numbers 1 through n. You first divide them into at least two groups or blocks.
Okay.
Then you look at each block. If a block still has two or more numbers in it, you have to partition that block again recursively into at least two smaller subblocks.
And you keep going.
You keep going, yeah, until every number is isolated in its own block of size 1. It's counting all possible hierarchical ways to group in things, always splitting groups of two or more.
That sounds quite different from trees, structurally.
On the surface, yes. But the underlying combinatorics, the way things branch or partition without simple one-to-one steps, it turns out to be the same mathematical structure.
Fascinating. And there were other connections, too.
Indeed. It's also related to series parallel networks. Specifically, it's half the number of series parallel networks with n-labeled edges.
Series parallel networks.
Yeah.
Like an electrical circuit.
Exactly like that. Foundational stuff in circuit design and network theory. And then shifting fields again, it counts singleton-reduced phylogenetic trees with n labels.
Phylogenetic trees, so tracking evolutionary relationships.
Precisely. Again, it's about branching patterns, specifically where you don't have a single lineage splitting off alone without immediate further diversification. It pops up in so many places.
Wow. Okay, so let's maybe look at the sequence itself. The numbers might give us a feel for this. The first few terms are 0, 1, 1, 4, 26, 236.
That's right.
That jump from any 3 giving 4 to any 4 giving 26.
Yeah.
It's quite steep.
It is. It shows how quickly the combinatorial possibilities explode. That value 26 for n-4 really illustrates the complexity.
So those 26 entries correspond to 26 distinct tree structures, or 26 ways to partition 1, 2, 3, 4, or related counts in networks and phylogeny.
Yes. Think about those tree structures using, say, bracket notation. For n4, you could have things like 12, 34, group 1 and 2, then group that with 3 and 4.
Or maybe 1, 2, 34, grouping 2, 3, 4 together first.
Exactly. Or 12, 34, all distinct structures, and crucially, no node just leads to one thing below it. It always splits. Those 26 structures capture all the allowed ways for n4.
It really drives home that series-reduced rule. Simple rules, complex outcomes.
That's the beauty of combinatorics. And connecting this to the bigger mathematical picture, we find things like recurrence relations and generating functions.
Generating functions. Always powerful tools.
Extremely powerful. The exponential generating function for this sequence, let's call it AX, it encodes the entire sequence, and it satisfies this rather neat equation, XPAX each 2AX plus 1.
SPAX equals 2AX x plus 1. That looks concise.
It is surprisingly elegant, isn't it? This single equation captures the recursive structure of all those seemingly different things, the trees, the partitions, the network connections. It's the mathematical heart of A000311.
So if you understand that equation, you understand the growth and structure of the sequence, and thus the growth of these complex systems it describes.
In essence, yes. It provides a deep structural insight.
Okay. So wrapping this up, what's the big takeaway here for someone studying number theory or related fields? Why focus on A000311?
Well, I think it's a fantastic example of mathematical unity.
Unity.
Yes, you have problems that, on the surface, look completely different. Drawing trees, partitioning numbers, designing networks, mapping evolution, yet they share the exact same numerical fingerprint.
The same sequence governs them all.
Precisely. It highlights this profound interconnectedness. Seemingly separate concepts are often just different facets of the same underlying mathematical reality. A 00003 of the 11 is a window into that reality.
It's like finding a hidden language spoken across different scientific domains. So the message for you listening is maybe to keep an eye out for these connections.
Absolutely. Explore the OEIS. Look for sequences that appear in unexpected places. You might be surprised by the patterns you uncover.
It really underscores that mathematics isn't just isolated formulas, but a web of deep, often beautiful connections. A great thought to end on. Thank you for unpacking that with us.
My pleasure. It's a truly fascinating sequence.